Good morning everybody, welcome to the course in the smart materials and intelligent system design. Now, in the last lecture I have covered the induced strain actuation modeling of magnetostrictive actuator. We have also shown that how to get the blocking force of magnetostrictive mini actuator. MMA means magnetostrictive mini actuator, that is the acronym. There are a lot of acronyms in this course and you have to be aware of them. Now, also we have talked about how to integrate the temperature effect, which happens as a result of passing current through the magnetizing coil to generate magnetic field, and we have noted down that how that adverse effect may create problem unless we actually integrate it in the constitutive relationship and take care of it, compensate this effect. Also, I have talked about two very similar kind of smart composites. One is called active fiber composite, AFC, active fiber composite, and the other one is macro fiber composite. These are of course made of piezoelectric material, but they behave in a similar manner as you put them in the magnetostrictive actuator. Now, in today's lecture I want to talk about the modeling of shape memory alloys, okay, which plays a very predominant role among all the smart materials, specifically because of its availability of large actuation strain, large actuation force, and also robustness of the system. So, there are many practical applications where shape memory alloys are used, and hence we let us put a focus on them. So, we will talk about forward and reverse transformation in shape memory alloy. We will talk about R phase transformation, constitutive models. Simple constitutive model we will take up, which is the Brinson model, and I will show you an experiment with shape memory alloy where to kind of give the concept of that shape memory alloy based control. As I have discussed earlier, that shape memory alloy based system, they actually go through two very important transformations. Also there are other transformations like R transformation, but the major transformation is what we will call the forward transformation of the shape memory alloy. So, forward in the sense that when it is getting converted from austenite to martensite. In this particular case, of course, we will see that this is a stress induced austenite to martensite phase. So, in this phase we will start with austenite here actually, okay. In the temperature diagram we do the other way around, and so that means we will start from here. So, this will be our austenite, this will be martensite. For temperature diagram we can show it with respect to high and low temperature, but this is a stress strain diagram. As you can see that this is the stress versus the strain that we are plotting. So, that means we are applying reversible stress into a shape memory alloy based system, and here we are starting then from austenite phase or the parent phase. Okay. So, there is a loop that we have shown here. Now, what will happen if you actually start to stress it at the austenite phase, okay, you will see that the modulus of elasticity is E A at the austenite phase. So, initially the stress strain diagram pretty linear, it will go like this until and unless it will reach this point 1. That is the starting journey where the stress induced martensite formation will start to happen into the system. So, this is where the phase transformation is occurring. So, this is also sometimes referred as pseudo elasticity, because you get actually a large deformation here that looks like a plasticity, but it is not, it will go back to the elastic region. So, the phase transformation happens at this stage. So, from 1 until I reach this point 2, beyond point 2 phase transformation is over, it will reach the martensite phase, but after this it will have its own stress strain diagram, and let us say we are not interested on that. So, from this point let us say I am actually reversing my stress. So, if I reverse my stress from here, then I am coming in down in this direction, and in this direction I have the elastic modulus, which is E m. The first of all, in the major loop part, one by one if we see in this particular region. Okay. So, if the 4 to 1, let us say, okay, 4 is the point where we will be actually coming back finally, as we will be applying reversing the stress. So, from 4 to 1, the stress strain relationship is something like this, which is a very simple linear relationship, that the strain will be proportional to the stress and the modulus of elasticity that will govern is E a. Now, as we go to the next phase, what will happen? We have to make a sort of interpolation between 1 and 2. So, we the maximum change of stress is sigma 2 minus sigma 1, the sigma 1 is here and sigma 2 is here, that is the maximum stress change. Okay. And what is the corresponding maximum strain change? That is lambda, that is the phase free strain that we call it. So, lambda over sigma 2 minus sigma 1, and now let us say I am anywhere inside this test point. So, at that point if the stress is sigma, then through simple interpolation I know what is the transformation strain that is there in the system. So, that is between 1 to 2, that is the relationship between this region, until the phase transformation is over, anywhere in this region, this will be the constitutive relationship in the system. Now, if I go to the conversion, reversion of stress. So, at point 2 there is a complete transformation to Martensite phase that has occurred from the austenite state. Okay. And then as I am reducing the stress, again first it will deform elastically, and so at that point you have this relationship sigma over E m plus whatever the free strain has occurred into the system. Now, depending on the position of sigma, you will be having actually reduction of stress. So, epsilon r will come down, and then once you reach point 3. So, we go back here, once I reach point 3, then the stress sigma 3 comes to the critical level, which will initiate the reverse phase transformation. So, austenite will then start to form. So, that is where austenite formation is starting, and austenite. So, Martensite to austenite transformation, again a sigma 3 minus sigma 4 interpolation you have to do. So, this is between sigma 3 and sigma 4. So, just like sigma 1 and sigma 2, we have to do this interpolation, and based on lambda free strain we will find out what will be the transformational strain at that stage. So, for this is the easiest one, based on the stress strain pseudo elasticity, the simplest constitutive relationship where temperature does not come into picture. You have actually 4 phase of this transformational system. First phase is this epsilon f equals to sigma over E a, that is the first phase, and then second phase where you are getting the transformation austenite to Martensite, and then you have the third phase when you are getting we are in the Martensite phase, and finally, the fourth phase where you are back from Martensite to the austenite phase. I told you that when you come back from the austenite to Martensite phase, let us say you are doing it not using stress, but using temperature. That means, you are simply cooling it. Okay. If you cool it, then also you will come back to the Martensite state, but there is a possibility that when you are actually cooling these what we call that from the austenite phase, you would see that there can be 2 candidate successors of lower entropy. It can either go to the monoclinic B19 Martensite phase, or it can go to the rhombohedral distorted Martensite, which is something like this distorted Martensite or the R phase. So, there are these 2 possibilities that is there in the system. If you look at it, say for example, in this particular case you are, let us say you are at the austenite phase. So, you are somewhere here, okay, and you are cooling it, phase transformation is occurring, and you can get this R phase into the system, and then you are getting to the Martensite phase. So, this is a smaller phase transformation. In fact, austenite to full Martensite phase transformation gives you about 6 to 7% of free strain. On the other hand, the transformational strain in the R phase is quite small, it is about 0.2 to 0.5%. So, that is why it is not very significant, but today people are coming up with some good thermal sensing, thermal sensor developments etcetera, based on the R phase. The yield stress for the Martensite phase is 200 to 250, whereas at R phase there is a lattice softening that is there. So, it is only about 5 to 25 megapascal, and thermal hysteresis however, in the R phase is much less, it is about 1 to 5 degree in comparison to A to R, which is about 30 to 50 degree centigrade for A to M. Okay. So, A to R is 1 to 5 degree and A to M is 30 to 50 degree centigrade. So, it has a smaller hysteresis, but it is a softened stage, its yield stress is less and the transformational strain is much less in the R phase transformation of the system. Now, knowing all these things that is happening in the SMA, let us try to actually develop a constitutive model. Let us try to see that what people have developed considering both stress, temperature and strain. There are various variations of this model. One of the most popular ones are macroscopic phenomenological models. So, these are based on phenomenological thermodynamics and are mostly defined using experimental data. Okay. So, there is a heavy emphasis on experiment in this case, and most of these models are developed for uniaxial loading. Now, if you want to refine it further, you can use actually microscopic thermodynamics model, which are based on microscale thermodynamics, that is phase transformations etcetera, that is happening in the system, and they are however so complicated that they are less amenable to include in the engineering analysis. Some of these microscopic thermodynamic models may need more than actually 30 parameters. So, in a real life or a real time analysis or a control system, it is quite difficult, although it is a very accurate way of actually defining the constitutive relationship of the system. There is also some micromechanics based hybrid macroscopic models. So, these are in between macroscopic and microscopic thermodynamic models. They estimate the interaction energy due to phase transformation of the material at the microstructure level using a group of some important variants and then include that effect in the microscopic level. There is also another group which is called quasi static macroscopic phenomenological constitutive model. These models use material parameters that are determined completely experimentally, mostly chosen due to their common approach and wide applicability to a large range of operating conditions. So, in our constitutive modeling, we will focus on the macroscopic and the quasi static macroscopic phenomenological models in our constitutive relationships that we will consider. Now, in this quasi static stage, there are three models that are proposed by people: Tanaka model, and then a slightly more refined by Liang and Rogers model, and further refined by Brinson model. So, firstly this model was developed by Tanaka and later modified by Rogers, and finally it is modified by Brinson in 93, and since then it became very popular, particularly for the analysis of shape memory alloy wears. Let us look at the Brinson model. So, if you look at the Brinson model, you will see that the stress strain relationship here is given in a differential form. Okay. So, now in that as you can see that the first part is the Hookean part, that is what is your common stress strain relationship that occurs every day type. Okay. Then you also have another part which is related to the pre stresses that happens in the system, which can actually you can include that in this, And then you have the second part here d dou sigma dou xi s, and xi s here that this xi s and xi t, these are actually related to two parts of stress induced and temperature induced volume fractions in the system. So, xi s takes care of the stress induced change and xi t takes care of the temperature induced changes. And finally, there is of course, the thermal stress that is there in the system. So, this part we would say is like a normal stress strain relationship. Okay. So, it is a common stress strain relationship, something like Hookean relationship, and these two parts are related to actually phase change, and the phase change has two parts in it. One is the related to stress induced change, another is related to temperature induced change, and this part is actually thermal. Now, the effect of this constitutive relationship can be also expressed if we consider this dou sigma dou epsilon to be kind of a slope actually, and then instead of differential form, if you want to actually use it in the form of a algebraic relationship, then you will get first of all in terms of d sigma would become your sigma minus sigma 0, where sigma 0 is the initial stress. So, this is the initial stress. Okay. Initial stress play a very important role, I told you, in the shape memory alloy based system. The slightly enhanced initial stress will give you better phase transformation. Now, that sigma minus sigma 0, then it is related to first of all E epsilon and then the initial stress part minus E epsilon 0. So, that is the Hookean stress strain relationship part. Then you have the phase transformation, and the first part of phase transformation is related to what you call stress induced transformation. So, this is stress induced. In fact, this is the contribution of Brinson. Otherwise, earlier it was simply omega times xi itself, the phase total phase transformation factor, but then xi minus xi at any stress and temperature minus xi at 0 stress condition, but then it is Brinson who actually divided these into two parts. One is the stress induced and another is the temperature induced. And finally, just like that last expression, you have this thermal part. So, that is what is the constitutive relationship that we will be using for modeling of the system. Now, how this constitutive relationship we can first of all visualize this whole thing. Okay. So, if we consider the stress temperature plot, earlier we have seen the stress strain plot, now we are considering the stress temperature plot. So, at the high temperature phase, what is the state we are supposed to see? The austenite state. So, this part is austenite, right, and as I am, let us say this is the austenite, and as I am reducing the temperature, okay, I will come first to this particular point, which is the Martensite stage. Okay. So, we come to the Martensite stage and then Martensite start and then Martensite finish. So, that means beyond this stage, if I cool it with no additional stress condition on this line, I will come back to Martensite stage. Remember that Martensite stage may have various variants. Okay. There are many variants of Martensite stage. Now, if I start to heat it up, what will happen? I will actually, so cooling is between these two. If I start to heat it up, I will actually start transformation from austenite start, and beyond austenite finish, I will be getting a fully austenite stage. What will happen if I now introduce stress into the system? Well, so you can see that these curves, okay, will remain similar, but from this point onwards there is a different behavior that you will expect. say for example, if I take any situation here, here we have a sigma s critical that is there. So, that means the stress induced transformation that has also started to take place. Okay. So, at this stage, if I am at austenite stage, okay, then I am actually cooling it, but there is some stress in the system. So, much before the Martensite state at 0 stress condition, somewhere here your Martensite will start to form, and then the Martensite will be finished. Okay. So, if I continue with this line beyond this point, it will be finished. In fact, it will Martensite formation will be enhanced if you come somewhere here. So, you can see that Martensite starting has further started from this point, and Martensite finish is over in this point. So, the entire transformation is happening much earlier than in comparison to the 0 stress condition. Now, what is happening when I am going back? Okay, when I am heating up the system, then also this curve, the slope of this curve is telling us that you are going to get the austenite starts. Let us say for this particular line, the austenite start is happening at this stage. Okay. So, that is where is my austenite start. Okay. So, with this particular stress condition, if I actually kind of enhance the stress further beyond sigma f critical, then what I am going to see is that the austenite state will start at a much earlier condition itself. So, then this particular thing is then telling us that if I, in addition to all other things, I have to also know the slope of these lines. Okay. These two lines are approximately parallel. So, that is defined by Cm, and also this other one is defined usually by Ca. So, that is Cm and Ca, that is the austenite line, that is defined usually by Ca. So, here we get a straight line, but here the relationship has these actually sloped lines here, and these sloped lines modify these temperatures, okay, because of the presence of the stress in the system. So, that is one feature that Brinson model has taken into consideration. Keeping all these points in mind, then when the when it is a condition where you have both stress and temperature, then for temperature greater than Martensite start. Okay. So, what you will see is that the forward transformation relationship when I am converting from austenite to Martensite, okay, and at that phase this is the relationship, okay, that sigma here is in between these. So, that means the Cm into T minus Ms, and here it is sigma f critical plus Cm into T minus Ms, and where your xi m and xi s and xi t, the stress and temperature induced transformations are given by these two functions. Now, when T is actually less than Ms, then you have a different relationship here. Here this is the xi s and this is the xi t relationship. Just simply based on this curve, if you actually work on, you will be able to get these relationships. Now, when temperature is in between Mf and Ms, okay, between Martensite start and Martensite formation finish is happening, and T is less than the T 0, then you have this temperature relationship that you will find in the system. Otherwise, this delta T zeta will be 0. And for the reverse transformation, for T greater than S, here it is C A, that this slope will come into picture, C A T minus A S, and here the stress in the phase transformation xi is related to xi 0 with this relationship, and xi has two parts, xi s and xi t. So, that is for the reverse transformation of the Brinson model. What when we actually try to model such a system, okay, and you have these CA and CMs etc. transformations. What is important is that we do not actually model them along a particular slope. Suppose this is the actual path, we model them by actually taking little increments in terms of the temperature first and then the stress, and again temperature and then the stress. That is the way we actually algorithmically try to follow the recovery path. In fact, that is what is the application of the Brinson model. Let us say I am starting from a temperature which is T 0, and I am starting from my initial phase transformation that is there in the system, and initial stress sigma 0 and epsilon which is free strain, and then I increase the temperature and then the stress del sigma. I calculate the xi for this new temperature and this new stress. So, we should call it sigma 1 here. So, for that I calculate it, and then that xi would become the new xi 1 would become xi now. I calculate what is the free strain recovery based on wherever we are at the xi 1, and then I can calculate what is the block strain. Okay. That means, if I try to stop this whole thing, what is the block strain that is coming into the system, and then I update the value of xi and store it to xi 2. That is the loop in which we will work until we follow the recovery path. So, there is another way in which this whole thing is done. Also, it is a simpler way in terms of applying this system in a finite element model. This was initially developed by Turner, okay, and based on nonlinear thermoelasticity. So, what Turner has shown is that you can describe this relationship in terms of two parts, where first of all your modulus of elasticity is temperature based, and then you have this stress strain relationship, and you have an additional thermal like relationship. Only thing, there is a negative sign here, because you remember that from austenite to martensite your system is actually shrinking during the phase transformation. Okay. From martensite to austenite, as you are heating it up, it is shrinking, and hence the temperature you are increasing, but the coefficient of thermal expansion is considered negative. So, that it is actually shrinking from martensite to austenite state. So, by using this kind of an alpha, which is known as equivalent coefficient of thermal expansion, ECT, equivalent coefficient of thermal expansion. Using this ECTE, you can actually model the relationship. So, that is another easier way, but this alpha you have to determine experimentally. Now, I will show you one such experiment. So, here you have the SMA wires and you have a beam, and let us say you are applying power to the SMA wire. SMA wire can be inside the system or it can be outside the system. Okay. So, and let us say the offset here in this particular from the geometric midpoint, let us consider a symmetric beam, that is about ds. We have considered here say various types of conditions here. So, beam is of acrylic material, elastic modulus is changing, okay, this little higher in this case, as beam thickness is also different 1.1, 1.8 and 2.8 beam width, and accordingly the flexural rigidities are changing. Okay. Now, what we are doing is that we are using this flexinol 125 micron wire, and we are studying how the offset is changing, how with respect to the change of offset the strain is changing in the system, and the deformation and the end point deflection is changing in the system. So, as you can see here that in this case the deformations, there are two of them, x deformation and y deformation of the tip point, that is happening as I am applying these power to the SMA wire. So, this is the SMA wire which I am actually actuating. Here I can show you that this is the experimental setup. As you can see that the SMA wire is attached to the beam, and we have a laser displacement sensor which is sensing that the tip displacement of the point. You can see this behavior in a small experimental setup. So, if I just show you, you can see that in this case there are two links in which we have this SMA wires in offset, and as I am increasing the temperature, SMA wire is getting shortened, and that force is actually the blocked force is actually bending these links, and as a result this tip point which we are tracking, in fact you can track it and you can create many different trajectories as a simple two link flexible manipulator system. So, this is how you can see that you can actually actuate such a system, and you can control the deformations, and as a result you can control the trajectory of any such point. This is a simple mechanism that we have developed which shows the application of SMA wire. Now, what we will be finding out is that as the offset is increasing, you are actually getting more and more end displacement. Okay. Both experimentally and theoretically we have seen that this is what is going to happen. Experimentally this is the peak, theoretically this is the peak. There is a bit of difference between the two, but it is true that with increase of offset end deflection increases. However, as you actually reduce as you further increase the offset, the tip deflection will come down. Why do you think this is happening? That the offset here, as you are increasing these offsets more and more, beyond a certain point what happens is that you need more stress, and that stress actually creates stress induced transformation, and as a result you do not get enough active strain, and hence the tip deflection is coming down in the system. This is an interesting part. These are the references that you can use for your further study in this course. So, this is where we will put an end, and we will learn about in the next lecture about the actuators and sensors based on high bandwidth low strain smart materials. Thank you.